Welcome all dear students of SIDC class. This is my fourth lecture regarding to complex number. In previous lecture we have seen about the algebra of complex number and number of problems regarding to complex numbers. In this lecture we are going to see the Argand diagram, then different form of complex number. First of all, what is Argand diagram? Complex number Z is represented as Z is equal to X plus IY. Here X is the real part of complex number, and this real part of complex number is plotted along x-axis, and hence x-axis is known as axis of reals, and imaginary part of this complex number is plotted along y-axis, and hence y-axis is known as axis of imaginaries. Here, see here, point P represent the complex number on this Argand diagram. But first of all, we have to see what is complex plane. The plane formed by x-axis and y-axis is known as complex plane. This is a complex plane. And any number represented on this complex plane is nothing but a complex number. In figure, point P of xy represent the complex number z plus x plus iy, where x is the real part which is represented on which plotted along x-axis, and iy is the imaginary part which is represented on y-axis. In this figure, again, this x plus iy is the general form, but we are going to consider a simple example. Let us consider a complex number z is equal to 3 plus 4i. Here 3 is the real part of complex number and 4i is the imaginary part of complex number. Remember, any point on x-axis represent the real number or real part of complex number, and any point on the y-axis represent the imaginary part of complex number. Here value of x is 3 and value of y is 4. Hence the complex number is z is equal to 3 plus 4i, which is represented by the point P on this complex plane of the Argand diagram. One thing should be remembered, that on a complex plane any point can be represent one and only one complex number. Then what is the application or use of this Argand diagram? Argand diagram is useful to study the complex algebra. Or we can say that complex algebra of complex number using an Argand diagram. Okay. In previous lecture we have seen that there are four different complex algebraic functions. One of them is sum, another is a difference, product, and division. Now, in this point, it is possible to study the sum of two complex numbers by using Argand diagram, the difference, product and division of two complex numbers by using Argand diagram. But before studying this, we should know the different form of complex number. Okay, first form of complex number is rectangular form. Rectangular form. This is the first. Here again, z is equal to x plus iy, and this is a complex number. In this complex number, x and y are the rectangular coordinates, and hence this form of complex number is called a rectangular form of complex number. For this purpose, again consider a Argand diagram. This diagram gives us OP square is equal to OP square, that is hypotenuse. This is a right angle triangle, is equal to x square, square of this side, and square of another side y square, or OP is equal to square root of x square plus y square, or we can write only simply modulus of z. Okay. The points P of xy, that is this point, represents a complex number z is equal to 3 plus 4. Remember that, again remember that a point on a complex plane represents one and only one complex number. The next form, polar form. One thing should be remembered, that by using the rectangular form, algebraic sum of two complex number and algebraic difference of two complex number is possible, but the product and division of two complex number, algebraic complex number, is not possible by using the rectangular form. For this purpose, the polar form and exponential form are necessary. See here, polar form. In polar form, in two-dimensional analytical geometry, polar coordinates r and theta and Cartesian coordinate x and y are used. This figure gives us the modulus and argument or phase angle. See here. From this figure, we can write cosine angle of theta, that is cos theta is equal to adjacent side, that is x upon hypotenuse r. This implies x is equal to r cos theta. In the similar way, we can find out the cosine of sine of angle this theta, that is sin theta. This is equal to front side y upon hypotenuse, or from this equation we can write y is equal to r sin theta. This figure also gives us r square, that is square of hypotenuse, is equal to square of adjacent side plus square of front side, that is x square plus y square, or r is equal to square root of x square plus y square. Okay. Now again we know that here the rectangular form of complex number is z is equal to x plus iy. Substitute the value of x and y. Here we get z is equal to r cos theta plus I r sin theta. Simplify this term, R is common, therefore R cos theta plus I sin theta, which is the value of R. This equation gives the polar form of complex number. In this equation, R and theta both are real number, but I sin theta is a imaginary part of complex number. Now, if Z is equal to R in bracket cos theta plus I sin theta is the polar form of complex number, then its complex conjugate will be Z bar is equal to R in bracket cos theta minus I sin theta. And from Z and Z bar we can derive modulus of Z, that is Z bar is equal to value of Z is R cos theta plus I sin theta into R value of Z bar R cos theta minus I sin theta. Simplify this term, we get R into R square in bracket cos into cos square theta, then cos theta into minus I sin theta minus I sin theta cos theta, then I sin theta into cos plus cos theta plus I sin theta cos theta, and last plus I sin theta into minus I sin theta minus I square sin square theta. Simplify this term, we get R square in bracket. This term and this term are equal and opposite, hence getting cancelled with each other. Now we have cos square theta plus I square is equal to minus 1 minus minus plus sin square theta. In trigonometry we know that sin square theta plus cos square theta or cos square theta plus sin square theta is equal to 1. Hence, modulus of Z square is equal to R square or mod of Z is equal to R. This R is nothing but the distance of point P from O, and this vector OP gives the position of point P from origin O, and this vector R is making an angle theta with X axis. Now, if this is the R is the modulus, then theta is the phase angle or argument. Just like R, we can calculate theta, that is phase angle. Here, we know that value of sin theta is equal to y upon r and cos theta is equal to x upon r. Therefore, sin theta upon cos theta is equal to what? Tan theta. Substitute the value of sin theta and cos theta, y upon r and x upon r. R get cancelled with each other, and we have tan theta is equal to y upon x, or theta is equal to tan inverse y upon x. This theta is nothing but angle made by this modulus with x axis. This is called phase angle or argument. Now, last form, exponential form of complex number. Third one. Okay. In order to derive exponential form, again consider a complex number in polar form, that is r cos theta plus I sin theta. According to Maclaurin series, e raised to n is equal to 1 plus n upon 1 factorial plus n square upon 2 factorial plus n cube upon 3 factorial plus n raised to 4 upon 4 factorial plus n raised to 5 upon 5 factorial and so on. If we substitute n is equal to I theta, then we have e raised to I theta is equal to 1 plus I theta upon 1 factorial plus I theta square bracket raised to bracket square upon 2 factorial plus I theta bracket raised to cube upon 3 factorial plus I theta bracket raised to 4 upon 4 factorial and so on. Suppose this is equation 1. Also, according to Maclaurin series, we have cos theta is equal to 1 minus theta upon 2 factorial plus theta square, theta raised to 4 upon 4 factorial minus theta raised to 6 upon 6 factorial and so on. Here also we can write this term, just rearrange something, 1 minus I theta bracket square upon 2 factorial. I square is equal to minus 1. Therefore, minus plus I theta raised to 4 upon 4 factorial plus I theta raised to 6 upon 6 factorial. Suppose this is equation 2. Also from Maclaurin series, sin theta is equal to theta minus I theta cube, theta raised to cube upon 3 factorial plus theta raised to 5 upon 5 factorial plus theta raised to 7 upon 7 factorial. Again here we can also rearrange and we can write I sin theta. I sin theta is equal to I theta plus I theta bracket cube upon 3 factorial plus I theta bracket raised to 5 upon 5 factorial plus I theta raised to 7 upon 7 factorial and so on. This is equation 3. From equation 2 and 3, we can write or add simply equation 2 and 3. After adding this equation 2, we get cos theta plus I sin theta is equal to 1 plus I theta upon 1 factorial plus I theta bracket raised to 2 upon 2 factorial plus I theta bracket cube bracket raised to 2 upon 3 factorial plus I theta raised to 4 upon 4 factorial plus I theta raised to 5 upon 5 factorial. Suppose this equation 4. If we compare equation 1 and 4, it is found that cos theta plus I sin theta is equal to e raised to I theta. Okay. If we multiply by r to both sides of this equation, then r cos theta plus I sin theta is equal to r e raised to I theta. What is this? This is the polar form of complex number. Hence we can write z is equal to r e raised to I theta. Here phase angle is exponentially, and hence this equation represents the exponential form of complex number in which r and theta both are a real number but e raised to I theta. This term is the imaginary part of complex number. In this way, we studied three forms of complex number: rectangular form, polar form and exponential form.